I'm also using a new mic. You guys can give me some feedback of how whether it's working or not working. I think it's working better than the other one. All right. All right. So I will give you guys a new homework assignment on Wednesday, after the homework assignment for Dijkstra's algorithm is done, because I don't want to give you two graph algorithms to work on at the same time. So that's going to be on Wednesday. Okay, on Wednesday we'll get another homework assignment for tracing the A star algorithm. So before I move on to predicate calculus, do we have any questions about the two algorithms that we have already introduced? One is called Dijkstra's algorithm, which is also what your homework is about, that is due on Wednesday. The other one is called the A star algorithm, which we talked about last Wednesday, and I performed a trace for that one too. So do we have any questions about either one of those algorithms? Okay, seeing none. Okay, so that basically concludes what we're gonna do about graphs, and we are gonna move on to predicate calculus. So predicate calculus is kind of interesting, okay, because there is the theory behind your predicate calculus. Okay, so this one talks about you know it starts with the explanation of prologue, okay, which is kind of fun. So we'll start with that. All right. Most of this, I would say all of it. Okay, so I'm not going to ask any questions about prologue or predicate calculus. However, I think it is useful to know about it. Okay, and I will show you, something about prologue as a programming language. So we'll talk about this as a language. And Wikipedia, as usual, has a pretty good summary of this particular programming language. It is an old programming language. It first appeared 52 years ago in 1972. Okay, so that's kind of a long time ago. But what is interesting about Prolog is in the 80s, this was the one of the programming languages for AI applications. So AI back in the 80s or even the early 90s is almost opposite to what we understand AI these days. So back in those times, AI is all about formal logic, symbolic processing, instead of kind of more fuzzy stuff like generative technology. I'm going to write you a whole English paper, that sort of thing. It's mostly about proving theorems in mathematics. So that's why, so that's, I think it's important to understand that, because right now we are making a full swing to neural net based AI as opposed to inference, engine type of AI. Okay, so one is focusing only on the logic, and the other one is for the most part focusing on neural net type of technology. All right. So are there any questions about what I just said? Yes. Um, it's almost like the entire approach is different. Um, okay, so I'll explain what Prolog is, in today's class. But to look at, Chat GPT, any type of LLM, okay, large language model, they are basically neural net based, which means, they use, a lot of data to basically go like, okay, if these are the words that I have seen already, what is likely to be the next word that I am going to likely to be the next words. Okay, but there's always a probabilistic element to the GPT technology, which means you can have the same prompt, okay, but it will give you different responses, even though the prompt has not changed. But in the case of Prolog and Lisp, also is another popular programming language related to AI. Those are symbolic processing, approach, which means if you ask the same question twice, it will always give you the same answer. And it's about proving things. It's not about you know finding patterns within things. Finding patterns within things is the specialty of neural network. The downside of that is, it's difficult to ask the neural network of, what you have discovered, because all that knowledge is embedded into the weights, between the neurons. So it's really hard to extract, what the neural net has learned. Do we know it has learned something? Yes. But do we know, can the neural network come back and say, okay, this is what I have learned and put everything in words? The answer is no, not that easy. So anyway, getting back to Prolog. Okay, so I have, here a Prolog engine. So let me save this file first, okay, because it has a lot of fun stuff that I want to save. So let me click save, and I'll just say cousins. Okay, there we go. And for now, I'm gonna save it, so only I have and logged in users can see it. Okay, so I'll save it like that. Cannot save, it already exists. Okay, so can I save it and in a different name? At least download it back to my own computer to put it to a place where I still have access to it. Okay. All right, so now that we have saved this file, we can create a new one. So go to here. I can just cancel this, create a program, and now we can create a new program. All right, so what I'm going to do, may be a little bit culturally insensitive because I'm going to make references to Star Wars. Is that okay? If anyone wants me to not make references to Star Wars, let me know now. Nobody? Okay, so I suppose I can translate those examples into something else. Um, okay, so it starts with what we call predicates. Okay, so this is a predicate. This is what we call an atomic predicate, which means there's no particular reason why this is true. This is what I'm telling you. It is true. Okay, so is a Jedi is the name of the predicate. In other words, it is, you can look at this as a function that always returns either true or false. Okay, but in this case, I'm going to say, Luke Skywalker. Okay, you'll just Luke here because there are no other Lukes in the movie. So in this case, this is a statement. Okay, it is a statement that basically says Luke is a Jedi. Period. Okay, literally. Period. Okay, there's no particular reason why Luke is a Jedi. We good so far? Okay, and I can have other predicates too. What color is Luke's first lightsaber? I think it's a blue one. Yep. Okay. So we'll say, has, use has as the name of a predicate to indicate that Luke has a particular lightsaber. We'll just call it blue. Okay. Just so that I don't have to type a whole lot of words. Is that okay? So even with only two, um, what we call, sentences already done, you can ask questions. So one thing that is kind of cool about your most Prolog implementation is it is interactive. So what you can do now is to say is a Jedi, but instead of using Luke here, you can say tell me all the people, all the characters that are Jedis, and Control Enter will can ask the question, and it says Luke is a Jedi. You go like, oh, great. Okay, we don't need a program to look at this code here and know that Luke is a Jedi. So now we can say, okay, can we add other Jedi's into this vocabulary sentences? So you can say, okay, another one who's also a Jedi is Obi-Wan. Okay, so Obi-Wan is also a Jedi. So once again, this is atomic, which means it does not rely on inferencing to say why Obi-Wan is a Jedi. It is a given fact that Obi-Wan is a Jedi. So now if I ask the same question again, it will say Luke is a Jedi, but wait, there are more possible answers. So when you click next, it will say that, oh, by the way, Obi-Wan is also a Jedi. Okay? So now we can, say, okay, Obi-Wan also has a lightsaber, and okay, Obi-Wan, and what is the color of Obi-Wan's lightsaber? Sorry, is also blue. Okay, just so that in this case, I'll call it green. Okay, I know it may or may not be green, but we'll call it green just so that it's different. Okay, and just possession, we don't know what blue is. We don't know what green is. They seem like just colors. So now we can say is a light saber. Okay, so blue is a lightsaber, and so is green. Because otherwise, those two tokens or those two words really have no particular meanings. So that's gonna have this is basically how Prolog works. Anything that is a token or an atom in the entire universe of this particular program starts with a lowercase. Only variables can start with an uppercase. Luke is not a variable, it is the name of one atom or one element of this entire universe. So it's Obi-Wan, so it's blue, so it's green, but other than these association using these predicates, there are no particular meanings. Okay? All right, so is there a Jedi that does not have a lightsaber? Or at least in the movies, that you Jedi does not have a lightsaber. Okay, so we'll just say that Yoda does not have a lightsaber, but he's still a Jedi, right? So we'll say is a Jedi Yoda. Okay. So now if you ask, who is a Jedi, it will give you three answers. Oh, okay. What did I? Is a Jedi. Oh, they need to be together. Okay, fine. Just syntactically, it wants all the predicates related to is a Jedi to be together. So now it doesn't complain anymore. Okay, a little picky. Okay, so now we have Luke, we have Obi-Wan, and we have Yoda. No big deal, right? But what if I want to be a snob and I say you are not a proper Jedi unless you have a lightsaber? Okay, so let's see how we can state something like that. So now we have another predicate, which is a proper Jedi. Okay, so we'll say X is a proper Jedi. This symbol means only if. Okay, so when you see colon with a dash, it means only if, which is kind of like looking at a implication, but backwards. So is a proper Jedi is what we normally see on the right hand side of an implication, and now the requirements is typically what we would see on the left-hand side. Okay, so the order is reversed when we try to specify implications in predicate logic in Prolog. Okay, so first of all, I think in order to be a proper Jedi, X should be a Jedi first, right? So we say, this X needs to be a Jedi first. But now we also want to specify that this Jedi owns or has a lightsaber. So how do we specify that? So now we specify that as has, okay, X has something called Z, and Z has to be a lightsaber. So now we say is a lightsaber Z. Okay, so right here, okay, we are looking at this and go like, um, can we translate this into language that we have already talked about? In other words, what is this asserting? This is basically asserting that for every element X in this universe, X is a Jedi. There exists Z such that X has Z, and Z is a lightsaber, implies X is a proper Jedi. So I know I just said a lot of words. I'll go ahead and try to capture that. I cannot remember how to comment in Prolog, so we'll look it up. So comment in Prolog. So a percent symbol followed by any sequence of characters to end of line. or the typical slash asterisk to do that. And your structured comment is slash asterisk. Okay, so that works. Righty. So we'll do that because I want to specify what this means. So this means for all x in the universe. So I'm going to use U to mean the universe. Universe is also known as a set. Okay, so in this case, the universe U is referring to all the lowercase things that are mentioned in this entire program. So that becomes our universe set. So for every x in the universe, there exists a z such that um, x is a Jedi. The comma in this case means and. Okay, so we have to say it now and x has z and z is a light saber. So we now that. So I have to look at the close paren here. This implies zx is a proper Jedi. I will format it so that you can see the entire thing. I will put in line feeds. Okay, so for every x in the universe, there exists a z such that x is a Jedi and x has set z and z is a lightsaber. If all of these conditions are met, if I can find such a z, then it implies x is a proper Jedi. So this portion here, okay, in the comments, what this is something that we have talked about already because we have the universal quantifier, we have the existential quantifier, we have conjunction, we have implication. So all of these are things that we already know how to express using the math format. It is expressed like this in Prolog. Do we have any questions about the meaning of this particular sentence? So everything that ends with a period is called a sentence in Prolog, which is kind of like a statement. Are we good so far? So now we can ask we can interactive ask again, and now we can ask who is a proper Jedi. Okay, press Control Enter, so that it will give you the answer. And now it would say Luke is a proper Jedi because Luke has a lightsaber called blue. Obi-Wan is a proper Jedi because Obi-Wan has a lightsaber called green. And that's it. Yoda is not a proper Jedi because according to this universe, Yoda does not have a particular lightsaber. Are we doing okay so far with this? All right. So this is the kind of like the essence of Prolog is it is really quantified expressions but encoded into what seems to be a program. Are we doing okay so far? Okay. Yes. It is an implication because this is not the only there may be other things that qualifies X as a proper Jedi. So which means you can also have another one here, which is a proper Jedi, and then you can now specify some different conditions. So that's why it is not if and only if, because if it's if and only if, it means that can be the only reason why somebody is a proper Jedi, but that's not the case. This is only one sufficient condition for someone to be considered a proper Jedi. Absolutely. All right. So are we okay so far? Okay. So another way to define a proper Jedi is, a proper Jedi hates all Siths, which is probably not true in the actual story, but we'll say that it is true. Okay. So now we have to introduce Siths into this entire universe. So is a Sith I guess Vader is a mandatory one. Okay, and and I know there are Siths who are not quote unquote bad. They are just kind of doing their own thing. Name one. How do you spell it? Okay, I can search for it. Sith who is not bad. All right. So according to this, Victivus was a businessman involved in mining. He's ruthless in business and held a vast wealth, maintains balance and decency in his life. So we'll call him Victor. How about that? I'm sure Darth Victorus is like what? But it's okay. So we'll just Victor. Okay. So Victor is also a Sith. All right. So now we want to express who hates whom. Okay. So we'll now say hates. Luke hates all, uh, Siths. Okay. So he hates his own father and he hates Victor. And we'll just say that Obi-Wan is the same way. Okay. So paste. So now we have Obi-Wan, Obi-Wan. And then now we have Yoda. So we say Yoda only hates Vader. There we go. In other words, there is one Sith that Yoda does not hate. Is that okay? All right. So now we want to introduce another predicate kind of like this. So we'll give it a different name. So we'll say is a, how would you call that kind of Jedi who hates all the Sith? Kind of black and white. Biased. Okay, I think that's the word. Biased. So it's biased. Just because somebody is a Sith, I automatically hate that person. I think that qualifies as a bias. So is a biased Jedi. Okay, very good. So X is a biased Jedi because that person hates all Siths, regardless of which one we're talking about. As long as that being is a Sith, I hate. Okay, so we have kind of the same logic here. Okay, X has to be a Jedi first. Okay, all right. So now our challenge is how do we specify that X hates all Siths? Okay. In other words, somewhere here I need to say X hates all Siths without fail. Okay. So the other way to look at this is it is not the case that there is at least one Sith that X does not hate. Let me say that one more time. Okay. X hates all Siths is saying the same thing as it is not the case that there is one Sith, at least one, that X does not hate. Is that okay? So now we need to specify negation. So now we can specify this is how negation is specified. Don't ask me why it is a backslash in the plus, but that's how negation is specified in Prolog. So we have to say it is not the case that um, X does not hate a particular Sith. So we'll say, it is not the case that X is not a universal Sith hater. Okay, so we can use that name as the predicate, not a universal Sith hater. Okay, whew, that's a long name. And now our task is how do we specify this thing here? So not a universal Sith hater X. So in this case, I don't really care about whether X is a Jedi or not. I just need to know whether there's at least one Sith that X does not hate. Is that okay? We good? Okay. So now we have to introduce an existential quantifier, basically saying, okay, so can we find at least one Sith is a Sith? We'll call that Z. And it is not the case that X hates Z. So we say hates X, Z over here. Are we doing okay so far in terms of the specification of not a universal Sith hater? So to kind of check out whether this code works or not, we'll kind of pop it into the interactive part of the Prolog engine. So we'll say not a universal Sith hater. And I'll just kind of give it an X here. In other words, name every um, person or every existence that is not a universal Sith hater. So we'll see what it comes back with. Okay, it might surprise you, and it is false. We cannot find a single one because we cannot find. Okay, wait, it's a Sith. There exists a Z, which is a Sith, and we know that Victor is a Sith, such that X. It is not the case that X hates Z, so that should not come back as a false. I'm a little bit baffled here. It cannot find X. So now we have to give it specific things. We'll give it Luke. False. Okay, that's expected. No, Luke is a universal. Okay, that's correct. So now we'll give it Yoda. Okay, so that is true. Now we can apply that to is a biased Jedi. Is a biased Jedi. And we'll say, is Luke a biased Jedi? The answer should be true. We'll find out. It is true. Obi-Wan is in the same boat. Obi-Wan, true. What about Yoda? And Yoda is not a biased Yoda. It's not a biased Jedi. So are we kind of getting the sense of how this can be useful? You can put in all the relationship in movies, TV shows, and they can give you answers. Great. Okay. So this is one example of how we can use predicate logic or Prolog in this case, but it is not really that interesting. Okay, because we are not doing anything that is recursive. The fun does not begin until you see recursion. So in this case, there's no fun in this particular program because there's no recursion. Okay, I don't see a whole lot of responses. Yes. Mm-hmm. Yes. Oh, not exactly. Okay, so that's a very good question. So anything that appears in the the consequent part of the implication is universally quantified. So in this case, x is universally quantified. But any variable that's introduced in the predicate of or the is it called the precedence of the implication, basically on the right hand, on what we normally see on the left hand side of an implication, those variables are automatically existential. So in this case, the z is existential, but the x is universal. Is that okay? So that was a good question. You almost caught me. Are we still doing okay so far? Kind of. Okay. So are we ready to look into cousin relationships? Okay, so let's do that. Let me see if I can save this. Um, we'll just call it Jedi. Okay, so this one saved correctly. Don't know what happened to the other one that didn't save correctly. All right, so we'll go ahead and close this or open another one, create a new program, and go back to the saved file. Okay, so we'll go ahead and check out whether that is saved correctly. Cousins. Okay, it is saved. So we'll go ahead and do an xclip cell clip cousins.pl and then just paste it back into here. There we go. Okay, I was working off of the Simpsons family tree just for fun. Unfortunately, that tree is very lopsided, so I can't really illustrate, what is a third cousin once removed or something along that line. So I'm going to create a new family tree, which is much simplified. So A is a parent of B, A is also a parent of C, B is a parent of D, B is a parent of E, C is a parent of F, and then C is a parent of G, and then we can work off of D, E, F, G now. So D is a parent of G, H, D is also a parent of I, and then okay, we'll just go for F here. F is a parent of J, F is also a parent of H, I, J, K. There we go. All right. And I'll remove all of this. Yeah, I wasted all my time a little bit earlier to put in all of those things, only to find out that I could not use that to illustrate the concept of cousins. Okay, so we only have a fairly small family tree here. Okay, in fact, it is just a tree. It is, I guess it's okay for amoebas, because they can do asexual reproduction. Everything only has a single parent as opposed to two. Okay, so in this case, if you look at this as a tree, let's go ahead and take a look at what it looks like as a tree. So as a tree, we have A branching to B and also to C. But B also has two children. One is D and one is E. C also has two children. C has F and G as children. And then D has H and I as children. E does not have any children, but F does have two children too. So F has J and K as children. Okay. So do we have any questions about the tree that is kind of ugly looking but in text format? Is that okay? Okay. All right. And if you want to use some symbols that makes it a little bit easier to read, I suppose I could do something like that. Okay. I'm not sure whether it's any better, okay, but that's kind of like a text tree thing, okay? Are we good so far? Because I kind of need to let you guys visually see what the tree looks like in order to talk about the convention of identifying cousins, okay? So in this case, can somebody tell me who is a second cousin of somebody else? Well, let's start with first cousin. What does it mean when we say that two things are first cousins in terms of ancestry? That's all we care, okay? It's just ancestry. So with a first cousin in this particular diagram, give me an example of two things that are first cousins. It's a trick question, by the way. There's none. There. Okay, go ahead. E and F. So E and F are, you're correct. They are first cousins because they are very good. Good job. Because their common ancestor is two generations ago, which is A. Okay, so now it's more clear why um, E and F are first cousins. D and F are first cousins. E and G are also first cousins. Okay. So cousins, so when you have the nth cousin, it means their common ancestor is n plus one generations ago. Let me say that one more time. So that means, for example, with first cousins, okay, two first cousins would have a common grandparent, but no common ancestor before that, because otherwise siblings can also be called first cousins. Nah, okay, siblings are not first cousins. Sorry, say again. They're zeroth cousins. Yes, you can name them zero cousins. Yep. What about the term removed? What does that mean? So when people say, these two are second cousins, one's removed, what does that mean? Between J and D. Okay, so between J, which is here, and D, which is over here. So they would be, let's see, I'm just counting here. They're second cousins, one's removed. Am I correct? I'm just, I need to count the correct number of, no, they are third cousins, one's removed. Okay. So the third comes from, how far J is away from the common ancestor. So J is 1, 2, 3 generations from the common ancestor. So that's why we call this, wait, let me say that, let me do this one more time. Yep, it's 3 generations. So it's a second cousin. But D is not of the same level in the tree. D is one level shorter compared to the common ancestor, so that's why it's called once removed. Are we doing okay so far again? Okay, so this may be a little bit culturally insensitive as well, because not every culture, makes the distinction of, how far are our first common ancestor, and then how far we are, the cousins away in terms of generations. So are we still doing okay with the terms? Okay. So now the question is, how do we code this? Okay, so this one is red because of what? Oh, I think it's just the cursor. Or is it complaining? Out of sync. I don't know exactly why it is out of sync. All right. So if you are to ask, who is a parent of whom, it will just kind of give you back everything that were listed in the facts over here. Syntax error because I did not. Oh, okay. There we go. Okay, ask it one more time. So it will give you all the pairs that we have seen here. XY can be AB, XY can be AC, can be BD. So it just basically reiterate or spells out everything that is captured here. So the first thing, the easier thing that we want to know is, how about ancestry? If I just want to know whether X is an ancestor of Y, how would I express that? Well, the first one, the most immediate ancestor, is a parent. So if X is a parent of Y, then X is automatically an ancestor of Y. Are we okay with that? Okay. But what about grandparents or grandparents? So in that case, what we need to do is to say, for every X and for every Y, okay, so universal quantifier, but the z is existential. In other words, we're basically saying, for every x and for every y, if I can find a z, there exists a z, such that x is the parent of z and z is a parent of y, then we can still claim that x is an ancestor of y. Does that make sense? So that's recursion, okay? This is recursive definition, because you can see how the predicate ancestor of is both being defined here, but it's also utilized here. So this way, we can, basically find out, okay, we can find specific things about this particular family tree. So you can ask, what is B an ancestor of K? The answer should be false, because B and K they do not belong to the same subtree. So the answer is false. Okay, very good. What about between B and I? Okay, they should be B should be an ancestor of I, and the answer is what? Oh, okay. I need to change it to ancestor of. There we go. So the ancestor of is true, but I want to go back to B and K because B is not an ancestor of K. So I want to double check and make sure that this is false. Okay, very good. So you can also list all the descendants. In other words, you can say, okay, if B is the common ancestor, I want to see all the descendants, regardless of how many generations after B. You can replace that lowercase character with an uppercase character, which basically means, okay, find me all the descendants of B in this case, and it will give you a bunch, okay? Because basically everything that is B, H, I, and E, they're all descendants of B. Are we doing okay so far? So I think we're starting to see something that's a little bit more interesting now because we can define things in a recursive way, which is kind of cool. How many people know SQL in this class? Okay. So now the question is, do you think SQL can also define recursive relations like this? Because in SQL, okay, this kind of relation, let me scroll back up a little bit here. This kind of relation can be established using a very simple, what we call an associative table. We just basically say, okay, this relates to this relates to this relates to this. So do you think in an SQL query, we can also define something along the line like this? Okay, it is a recursive definition. The answer is yes, which is really, really kind of cool. Okay, because you can now define categories and you can define subcategories, you can define subcategories of subcategories and so on. And in a single query, you can say, does this thing belong eventually to this particular overarching category? The answer is yes, it can actually find that out. So it's a kind of useful way of applying what we see here to a practical application in database management. Okay, so this is all good, but this type of definition of ancestor of or ancestry, check, is not helpful if I want to confirm, whether a particular entity is the nth cousin of some other entity, x, many levels removed, because it doesn't do any counting. All it can do is to go like, do they have a common ancestor? Yep. But where is the common ancestor? We don't really know. Okay. So that means, we kind of have to define something like this. So we still have ancestor of, but this time there are three tuples. The parameters is a three tuple, which is including um, a number. So in this case, in the first definition of this particular ancestor of, it is saying, X is an ancestor of Y one generation away. So this one here is a constant. Now, if you don't like the use of constants, you can always say, N over here, and then you specify, and by the way, N is 1. Okay, you can specify that. But, that's really not necessary. So I just put a 1 here. Are we good so far? Okay, so ancestor of XY1 is really just looking for parent-child relationship, but then we have N here. In other words, if I want to confirm that X is N generations away from Y being the ancestor, then we need something similar to what we already have before. X has to be a parent of Z. There exists a Z such that X is a parent of Z. And then we define M over here, and M is a existential quantifier, which means M is, we just have to find M such that M itself is N minus 1. And on top of that, Z is a ancestor of Y M generations away. So this is how we can say, oh, okay, so combining the parent-child relationship between X and Z and the ancestor relationship between Z and Y, X is now N generations away from M because M is only N minus 1. Okay, is that okay? Yep, go ahead. So if it's a zero, then it will return false. Because if it's a zero, that means x and y on x is not an ancestor of y. X and y are the same. So I'm okay. At least in this program, I do not consider a person as the zeroth ancestor of the same person. So you cannot be your own ancestor. There's no time loop um, paradox in this case. All right. So now we can go to cousin or define cousins here. Z is not really needed. I only defined it for debugging purposes because Z is the common ancestor of X and Y. And basically, this is saying X is the nth cousin of Y, removed or removed. Okay, you can removed is a number. Okay, it's basically indicating how many generations removed. So the way it works is the first thing is I know that if we're talking about first cousins, it means their common ancestors are 2 generations ago. So I define C, which is just nth plus one. Then M, which is referring to the common ancestry or the distance of the generation gap between Z and Y, that's going to be C minus removed because that's what removed is trying to specify is they are different, they're on different levels of the tree. Okay, so we have to take that into consideration. And then we want to confirm that Z is an ancestor of X C generations ago. Z is also an ancestor of Y mth generation ago. But if I stop here, then we can end up with a situation where they also have common ancestry before Z, and that would not be right, okay? Because we need Z to be the first common ancestor, in this case. So the way I take care of that problem is to define C1 to be C minus 1, M1 to be Mth minus 1. And then once again, this is a negation so that we can say X and Y do not share a common ancestor, that is for X, C1 generations ago, for Y, it is M1 generations ago. So we are trying to detect and make sure that there are no common ancestors until we get to Z. All right. So I haven't tested this one yet, okay? Because when I was writing this code, somebody came to my office and asked some questions. So we give it a test. So now we can say cousin, and Z remains as a variable, okay? And then we just have to name the two items in this tree here. So we'll take a look at what we just mentioned earlier. We'll compare J to D, and they are going to be, let's see, two second cousins, one removed. I think that's what they're supposed to be called. And A is the common ancestor. And I think that's the only answer. So if I click next, it would just return false. Are we doing okay so far? So what if you want to specify just regular cousins and without the removed? So now we can say, okay, so we can now ask, this one does not allow a lot of variables, so I can see if this works. J is okay, it still works. So H is also a second cousin of J. So H is over here and J is over here. They are second cousins because their common ancestor are 3 generations ago, and there are no common ancestors in between. So now you can check, okay, what if there is a common ancestor in between? Is it going to catch it? So the best way to look at this one is H and I. Okay, so you can say H and I are the second cousins from the perspective of A. because A is a common ancestor, right? A over here is a common ancestor, 3 generations compared to H as well as I. But their immediate common ancestor is D, and then they also have a common ancestor of B. So that this means the answer to this question should be false. So that's basically, I'm only showing you a very small portion of what Prolog can do because Prolog can also deal with lists, which means it can actually handle complex data structures, but not in the same sense that you guys understand data structure in CISP 430, because everything has to be a list. You can have an item in a list that is also a list, so you can have nested lists, but you do not have anything that even closely resembles, not even remotely resembling objects. So it doesn't have key value pairs, as far as I know. So we okay so far with what Prolog allows you to specify. Okay, so let me go to one of these things here, and kind of reverse it and specify how we would have otherwise said the same thing. So we'll go ahead and basically say, what does this mean? It means for all x, y in U, there exists a z such that x is a parent of z and z is an ancestor of y. And if that is true, then we can say that x is an ancestor of y. Is that okay? So the translation, there's a direct translation between sentences in Prolog and the quantified expressions that we have basically talked about since the beginning of this entire class. And the beauty of Prolog is it does backtracking automatically. So it will give you all the possible answers, unless you specify what we call a cut operator, which means I just need one answer. Don't go back and give me any more answers. Then it will stop going back and backtrack and give you more answers. Does everybody understand what I mean by backtracking? Have they talked about that term in CISP 430? Backtracking? Okay. So backtracking means consider that you're in a maze. Okay, so you're in a maze. There are multiple pieces of cheeses. Okay, with somewhere in the maze, and you're a mouse. Okay, so with without backtracking means you are just going to find the first piece of cheese, and you go like, yes, I found the cheese. I'm done. Okay, with backtracking, it means you found the first cheese, and then you're going to go back to the first intersection where you have only explored, where you have unexplored branches. Then you go to that unexplored branch and say, I hope this branch also lead me to another piece of cheese. Okay. And it will basically use this mechanism to find all cheeses, all the pieces of cheese in the maze. So that's what backtracking means, is you go back to an earlier point and then go like, have I explored this branch? If I have not explored this branch, I'm going to explore this branch now. It is also closely related to depth first search. Has that term been introduced in CISP 430? Depth first search. Okay. So basically, what Prolog does is it will automatically perform a depth first search to find all possible answers that will meet a certain criteria that you have specified. Now, if you specify the criteria, or if you want to say, okay, this is exactly what I need to determine, is it true or not, and everything is not a variable, then it just goes like, okay, I'm just going to check this one thing. But if you give it variables, then it will go like, okay, let me find all cases to instantiate these variables, and they still meet the requirement of whatever is specified. Is that okay? All right. So there was a time when this is considered the epitome of AI, artificial intelligence, because at that time the focus was automated theorem proving. Okay, which is a very narrow field. Okay, because all we want to do is to prove mathematical theorems. Then you guys go like, but Tech, didn't we talk about propositional logic or propositional calculus? Doesn't that automatically prove theorems already? The answer is yes. Okay, propositional logic is designed to prove theorems or to prove arguments more precisely, but it cannot handle quantifiers. And predicate calculus, which is also called second order logic, handles quantifiers. Propositional logic also is called first order logic because it does not handle quantifiers. But you can also see why quantifiers are important in this case because you're not only talking about specific who is whose ancestor. I want to find all ancestors, and the ancestor definition itself is also recursive in this case. So do we have any questions about these examples? You go ahead and then, yep. hmm Sure. So without backtracking, okay, so let's just say that we want to find, who is whose ancestor. So without backtracking means I can use what we call a cut operator. The cut operator is also known, is the exclamation point, symbol here. So that means, as soon as I find the first ancestor, it's going to stop. It will not go back and say, hey, are there other cases, that we can go back to and then re-explore. You can also put a cut here. That means if I find, so in this case, okay, let me check because I just want to confirm that my understanding is correct. So in this case, if I just say, okay, give me all the descendants of A, okay, like so, then it goes like B, done, because the cut operator is right here. The moment it sees that A is B's parent, it goes like, okay, we're done. We found one descendant of A, which is B, and we're good. But if I remove the um, cut operator from both of these, then the same question is going to generate a bunch of answers because now the entire subtree are descendants of A because A is the root of the tree. So that means everything after A, B, C, D, E, F, G, H, I, J, K, they are all descendants. So is that help? Okay. hmm Any other questions? Oh, you had a question earlier. Go ahead. Yeah. Yeah. Aha. Okay. I see what you mean. So let me save this one first. I think I might have a program of the same name. That's why it's complaining. Yep, that's why. So let me save it in under different name. Cousins 2. There we go. So we go back to Jedi. Okay. And your question was, it does not have the understanding of a set, but it does have an understanding of a list. So there are ways to go through a list, and the way you go through a whole list is the the mechanism of how Prolog handles a list is very similar to how Lisp, LISP, which stands for list processing, handles a list. Basically, you can separate the first item of a list from the rest. So the first item is now the one single thing that you can focus on. And if that thing does not meet what you need to do or does not, for any reason, answer the question, then you can recursively use the rest of the list, in the recursion. So you can simplify the way we define things here so that you can have, you know, is a group of Jedi's and then give it a list. So this way, we can save all of these things. And then is a Jedi um, it becomes a recursive definition making use of the list. So yes, the answer is yes, you can, we can do it. It's just, I don't want to introduce data structure in Prolog. Mm-hmm. Mm-hmm. You could do that. Yep. Mm-hmm. In other words, if you want to specify that, that Luke hates all Siths, you can make a predicate for that. And that's the other thing that you can do in Prolog that's very easy, which is doing something like this. Is a um, you can say hates, uh, but you have to qualify all the Siths too. So yep. Hmm. Okay. So if you want to use a predicate to assert that Luke hates all Siths, then let's see how we can do that. So we'll say Luke hates all Siths. X. So now we have to look at all the Siths, but you cannot confirm all the Siths, but you can confirm the negation of an existential quantifier. So that's why it comes in handy to do something like this. But then you're looking for the lack of a counterexample, and that's the only way you can specify something like what we are trying to specify. So so does that address your question? Okay. Are there any other questions regarding Prolog? No questions. Hmm. All right. So do you think we can use Prolog to find the shortest path, or at least the length of the shortest path between two vertices? And if so, how do we do that? Let me see if I have the solution already saved, because I think I might have worked on that one already. So we'll take a look at, okay, there's nothing recent. Okay, we can work on it. All right, so save this one first. No, we don't want to save a new version. So how do we just save it? Guess it's automatically saved. Okay. All right. So the first thing we need to do is to encode the edges and also the distances between edges. Okay. So that's rather easy to do. Okay. So I will do both at the same time. So edge is going to say, whether there's uh, it will state the what we call the tail of the arc, okay, which is where we're coming from, and then the head is where we're going to. I know it sounds kind of reversed because the tail refers to the tail of an arrow, and then the head is also referencing the head of the arrow, and we normally associate an arrow as going from the tail to the head, so that's kind of where the terms comes from. All right, so for this, let me see. We can go back and use our homework assignment as the source of this data. So we go back to Dijkstra's algorithm, and then we basically just convert D into its own list of predicates. So I'm going to do that usual trick, but it's not going to work because this extends out to over there. Hmm. Okay, now it works. All right. All right. So now go back to Prolog, and I'm just going to encode this entire thing. So we have CA4, we have CD2, DB1. And by the way, are there any questions about the homework assignment that's due on Wednesday? It's basically tracing the algorithm. No questions? Okay, all right. BA1, and the next one is EC3, FE1, FB8, GA2, oops, and lastly we have AG1. Okay, so what I have done so far is really just encoding the edge and also the distance of an edge. Yes, I'm kind of merging those two things into one thing, which is okay. Okay, I'm just kind of shortcutting a little bit here. All right. So the first thing is, if I, so basically I just want to get a warm up of, okay, can I at least find out whether a vertex is connected to another vertex, maybe through multiple hops. Okay. So that's the first thing I want to find out first. So we'll define it as reachable. Okay. So reachable is going to say, okay, is X and Y reachable? Is Y reachable from X basically? So well, the first one is, hey, if I can find an edge between X and Y, we are good. We are solid. Does that make sense? Okay. But what if that is not true? In other words, there's no single edge between the two vertices, which are in the variables X and Y. Well, then we have to go for the recursive definition. X and Y is reachable from X only if there is an edge between X and some vertex Z, and Z itself can reach Y. Is that okay? So once again, we are using a recursive definition. That's kind of like what we had before, when we talk about ancestry. But there's one problem here. Okay, this can lead to um, an infinite loop, because there's no way, okay, at least the way I implement it right now, I am not remembering, all the vertices that I have gone through already. So it can go through an infinite loop. Okay, just to illustrate that, let's go ahead and find out, um, what an infinite loop will do to this. So what is an infinite loop in this case? A and G, okay? So we'll talk about A, G, and then we just say, okay, um, edge, uh-oh, AB does not exist reachable from AB. Oh, right, because I have to specify the distance. So the distance is not important in this case, so I can use an underscore to replace that. So there we go. There. So A and G are reachable, but it finds the answer and then it returns right away, because it doesn't. The recursion is checking for. This is the order, okay? This is the order of how things are evaluated. So if AG meets this one, then it doesn't need to go for the second one, which means it returns right away. Go like, okay, we're done. A and G are connected. So we have to look for something that's indirectly infinite, and I'm not sure whether this one has it or not. So CA, nope, GA, nope. D to B, B to A. Does A go back to D? We're looking for a loop. Okay, so I don't have a loop in this case, but you can also ask, what is reachable from A? Okay, so I don't think this is leading to an infinite loop. Oh, it does. You can see how, things that are reachable from A is A, G, A, G, A, G. Basically, it is going through multiple iterations of the loop. It's like, look, I got back to A again. Look, I go back to G again. but the path is getting longer and longer because it's basically repeating those two arcs. So now the question is, how do we make sure that this doesn't happen? That it looks for other things that that are also reachable from A. Unfortunately, there are no other things that are reachable from A. So let's try CX here. In other words, we're asking what things are reachable from C, because the loop can basically lead the algorithm to only go between A and G. And so let's see whether it's missing something that should also be reachable from C. C can go to D, D can go to B. You can see this loop here does not include B. So we go like, that is a problem, because it ignores certain alternative paths because of the way this recursion works. Okay, so how do we solve that problem? You basically have to say in X number of hops what is reachable. Okay, so that's the first thing we need to do, is to say, is something reachable within n hops? One hop is following one edge. So if something is 2 hops away, that means it is 2 edges away. So now we can define a different reachable, which is xy, but we also specify within n hops. So now this one says, okay, um, we need n to be greater than 0. Okay, well, okay, we can have an edge between x and x itself. So that's the first one. Okay, so basically we're looking for lack of a better term, reflexive edges. Okay, basically a vertex can go back to itself, and I don't even care about the distance at this point. Then we say, okay, if a vertex is not going back to itself, okay, x and y, nope. Okay, so I think in this case we need to specify x, y, but we also need to make sure that n is at least 1. So we have to say n is at least 1. This is how you specify greater than or equal to. It needs to have the at symbol. So if this fails, which means we cannot find a direct edge between x and y, then we have to go for the recursive case. So the recursive case goes like n this time has to be greater than or equal to 2, and then we have n1 is n minus 1. Then we specify edge xz, and then specify reachable z y. Oh, this is supposed to be in comma here, and 1. Okay, so this new reachable definition, you're basically referring to these two. They are essentially the same as what we had before, but now I specify an upper bound of the number of hops. So I can say within 3 hops, okay, what can I reach? So that means the graph can still contain loops, okay? It will still go through the loops, but it will only go through the loops within the specified number of hops. Is that okay? So let's try this out. Okay, we'll try out the same thing. Give me everything that is reachable from C, but we only look for one single hop, which means I need a direct edge from C to something. Okay, and see what those vertices can be. So now we say A is one answer. Okay, and this is not going to be an infinite loop anymore because it will exhaust every loop that is within, guess what, one hop. So let's see if this answer is correct. C can go to A as a direct edge, yes. C can go to D as a direct edge, yes. Okay, not a problem. But you can see that the loop is gone for now. So let's see, within 2 hops, what can we do? Where can we reach? A again, and then D, G, and then B. Okay, so within 2 hops, the original answer A and D is kind of obvious because they're all within just 1 hop, but then the G and the B doesn't make sense. So I can go to A and then A can go to G. Okay, so within 2 hops I can get to G, and within 2 hops I can also get to B, because C can go to D and then D can go to B. So within 2 hops, I can also get to B. Is that okay? So if you specify more hops, enough hops to start to contain a loop, it will give you kind of repetition of the answers. So if you say within 4 hops, now we start to see the loop. Okay, because within 4 hops, it means I can go from C to A, and then A to go to G, that's the second hop, and then G back to A, which is the third hop, and then A back to G, which is the fourth hop. So that's how this works. Are we doing okay so far? All right. So how is this going to help us being able to specify an upper bound on the number of hops? Well, it immediately helps us with one thing. Okay. Um, how many? Okay, let's just say that we have n vertices of the entire thing. Okay. So what would be the longest path in this graph that does not involve a loop? How many hops would that path be? It would be n minus 1, exactly. Okay, so that means I have now a mechanism to be able to look at all the paths without having to worry. I can guarantee to examine every single path because of the nature that it only goes to a certain number of hops. And if I have n vertices and I specify the number of hops to be n minus 1, then I guarantee that I have a chance to look at every single path. Now, would some of those paths be involving loops? Yes, it would. But the question is, would a would a path that is going, okay, by definition, you cannot have a path that has a loop, but I'm just using the term path loosely. Okay. So if a path involves a loop, it's basically going between 2 vertices again. Okay. Do you think it will be the shortest path? No. So that means, yes, I would still be wasting time to evaluate, traversals that has a repetition, but I won't accidentally use those as the shortest path, which is great. Okay. Um, so now I can say, okay, but what about in terms of the number of hops? Okay. In other words, I want to find the shortest number of hops to get from one vertex to another vertex. Can I do that? And if so, how do we do that? Let me post the question again. We are running out of time, but you can think about the approach. The syntax, may be a little bit new. You may not be able to complete the program, but let me just ask you to think about this, and then on Wednesday we'll talk about it. So I'm asking for a way to find the shortest number of hops between 2 vertices. So there may be 2 paths, okay, from one vertex to another vertex. One involves 3 hops or 3 edges, and then the other one involves 4 edges to go from one vertex to the next. I just need to find the smallest number of hops between those 2 vertices. So how can we do this? In other words, I'm trying to do repetition, increasing the number of hops as necessary until I go like, okay, wait, I can stop here because I just found a path between this and this with this number of hops. I don't need to increase the upper bound again. Okay, so think about how to specify that in predicate logic, because it's programming, but it's a very weird way of looking at things. So that's the first thing you need to do, is to kind of change your perspective of how to specify what we normally see as iterations, because iterations can only be done using recursion. Recursion is the only way for repetition in this kind of programming. Is that okay? All right. So we'll go ahead and continue this on Wednesday, which is also the same day that I'll give you a new homework assignment on the A star algorithm, which is going to be due in a week, which is next Wednesday, which also, by the way, is the last lecture of this class. So we have 1, 2, 3. We have 3 lectures left and then the final exam. All right, I'll see you guys on Wednesday. Ooh. Oh yeah, I can send it like right now. Yeah. Yep. I I may not have run it.